Okay. So let's say we have a 2x2 matrix. Let's start with a little small matrix. We have 2 rows, 2 columns. We are now going to be looking at a characterization of these matrices. We're going to do a calculation that is going to allow us to compute what is known as the determinant of a matrix. We can denote finding the determinant of a matrix by just writing DET of open parentheses, whatever matrix we're finding the determinant of, or I can just write DET of the matrix and not put the parentheses around the matrix, or, which you will have to recognize, I could just put these bars on either side of the matrix. Now, this is not to be confused with finding the absolute value. That makes no sense. Absolute value is distance. We don't have distance with respect to matrices. Matrices are data. They're just elements. They're just data. So if you see these bars around a matrix, you need to, on that test, you will need to know I am asking you to find the determinant of the matrix. Now, we can only find the determinant of a square matrix. If you a matrix that doesn't have the same number of rows as columns, and I ask you to find the determinant, you will have to write on the test, cannot compute the determinant, it is not a square matrix. So yet another rule, right, for you to be aware of. So let's say I do give you a square matrix and I ask you to compute the determinant. How do you do it? It's very simple. All you do for a 2x2 matrix is multiply the numbers on the main diagonal, multiply the numbers on the cross diagonal, and subtract them. That's it. That's all you have to do. So you multiply the numbers on the main diagonal, you multiply the numbers on the cross diagonal, and you subtract them. And this is for a 2x2 matrix. There's a different process for larger matrices with higher dimensions. So let's look at a few examples. Let's say I am asking you, I'm giving you this matrix A, and I'm asking you to compute the determinant. And again, I'm denoting that in this case. So if I give you a matrix on that test and say, find this, you need to know what I'm asking for. What do? You multiply the numbers on the main diagonal. So that would be 1 times 8. And then you subtract the product of the numbers on the cross diagonal. So that would be 4 times 5. So that's 8 minus 20. So the determinant of A would be what?
Negative 12.
Okay, so we got it. We got it. Excellent. So that would be negative 12. All right, let's try the next one. I'm giving you the matrix B and I'm asking you to compute, notice that, I'm just saying find that. And you have to know that means I'm asking you to find the determinant. Look at the main diagonal, multiply those elements, subtract the product of the cross diagonal elements. And what is that going to give me? This is just 1 minus a half, right? What does that give me? Wow. Wake up.
A half.
0.
A half. Okay, let's try the next one. Again, a nice little 2x2 matrix. I'm asking you to compute the determinant of that matrix, multiply the elements on the main diagonal, subtract the elements on the cross diagonal. Okay, so that's going to give me 1/2 times 2 pi is just pi, right? Minus 4 times 1/8 is just 1/2. Now, can I do anything else with that?
No.
No, that's the determinant. We don't let pi equal anything and keep going. No, that's it. All right, C. see how we are going to compute the determinant of a 3 by 3 matrix. Now, if I give you a matrix that's even higher ordered, a square matrix that is 4 by 4 or 5 by 5 or larger, you're going to do that on the calculator. You enter in the matrix, you go to calc, the very first thing is DET, that's the determinant of the matrix. But if I ask you to do it by hand, and you know I'm going to ask you to do it by hand, let's talk about how we would do that. Well, it's similar. We are going to start by taking the matrix, taking the matrix, and we write the matrix as is, but then we repeat the first two columns. So take the matrix and repeat the first two columns. Then, along the same lines, I'm going to look at products of diagonal entries. So I have my 3 diagonal entries. I'm going to take the product, 2 times 2 times 8, 4 times 3 times 1, 1 times 5 times 4. But what I'm going to do to these is I'm going to add them. Okay, so that's going to give me 32 plus 12 plus 20, which reduces to 64. But I'm not done yet. I'm going to take that value, and now I'm going to look at the cross diagonals. I have this, this, and this. So again, I'm going to take products 1, 4, 3, 2, 8, 5, 4. I'm going to add those, and I'm going to get a sum, but then I'm going to subtract that sum. So let's keep going. I'm going to have 2 plus 12 plus 160. That's going to give me 186, but I am subtracting that value. So the determinant of D is what? You tell me. Perform that. What is the determinant of D?
Negative 122.
Negative 122. Excellent. Okay. So again, you append the first two columns, and then you look at diagonals, product plus product plus product, and then you subtract product plus product plus product. That's it. Higher ordered, you do on the calculator. Now, why are we finding the determinant? Well, we talked about matrix operations, addition, subtraction, scalar multiplication, matrix multiplication. Well, you can't divide by a matrix. You can't divide by a matrix. Instead, what you're going to do is you're going to multiply by the inverse. Think of the inverse of a real number as the reciprocal. The inverse of a matrix is how you are going to perform that division. Make 1, right? Okay, so how are we going to find the inverse of a matrix? Well, the first thing you want to do is you want to calculate the determinant. Because if the determinant is 0, there is no inverse. That's important. Let's go ahead and specify that now. You can only find the determinant of a square matrix. However, not all square matrices have inverses. If the determinant of a matrix is 0, the matrix has no inverse. We call it non-invertible, but more importantly, and more often used, we use the term singular. If the determinant is 0, there is no inverse, we call the matrix singular. It's not invertible. It's non-invertible. So if you calculate the determinant of your matrix and it is 0, you can't take the inverse. So if I give you a matrix and it's not square, you can't take the inverse. You can't find the determinant. If I give you a matrix that's not square, you can't find the inverse. If I give you a matrix that is square and the determinant is 0, there's still no inverse. And you would have to justify there is no inverse because the determinant of the matrix is 0. So these are all the justifications that we're going to have to include on the test to get full credit. Now, let's say I give you a square matrix, you compute the determinant, and it is not 0. Then we have to go forward and we have to find the inverse. It is invertible, and we call that matrix non-singular. How do we find the inverse? Well, let's look at a 2 by 2. First thing you want to do is compute the determinant. Let's say you compute the determinant and it is non-zero. To find the inverse of a 2 by 2 matrix, and we denote the inverse of A, matrix A, with that little superscript exponent of -1. Because we know how to address negative exponents with real numbers, right? A number raised to the -1 power, it drops to the denominator, so it's 1 over that number. So the same thing here. To find the inverse of A, I'm going to take 1 over the determinant. That's why it can't be 0, because anything divided by 0 is undefined. Now, we are going to multiply 1 over the determinant by a very special matrix. It's called the adjoint matrix, but that's not the important part. To get that special matrix that we are multiplying 1 over the determinant by to get the inverse, notice what you are doing. You are interchanging the numbers on the main diagonal. Do you see that? You are interchanging the numbers on the main diagonal. Then you are negating the numbers on the cross diagonal. That is how you compute the inverse of a matrix, of a 2 by 2 matrix. So let's look at an example. You are given the matrix C. You are asked to find the inverse, and it's denoted that way. I'm not going to say find the inverse of C. I'm going to say find this, and you have to know its inverse. The first thing you want to do is compute the determinant of that matrix. Again, notice if it has the bars around the matrix, that means determinant. So let's find the determinant of that matrix. To find the determinant of the C, remember, we are just looking at the numbers on the main diagonal. So that's 6 times -2. And then we subtract the product of the numbers on the cross diagonal. So that's -12 plus 14, which is +2. So can I compute the inverse? Yes, the determinant is not 0. So once I find that, I can go ahead and compute the inverse. Oh, heavens. I can't adjust that. That's terrible. Okay, let's find the inverse. The inverse is 1 over the determinant times that special adjoint matrix. What is the adjoint matrix? What did we say to do? Interchange the numbers on the main diagonal and negate the numbers on the cross diagonal. So what is that matrix? Tell me. You tell me.
-2, 2, -7, 6.
Excellent. And then I just performed scalar multiplication. So that's going to give me what matrix? Do I need to write that out? -2 divided by 2, 2 divided by 2. I'm just doing scalar multiplication. What does that give me?
-1, 1, -7 over 2, 3.
And that is your inverse. Exactly. Excellent. Excellent. Now, some special properties of inverses. Some beautiful things about inverse. Well, let's first recall what the identity matrix was, the multiplicative identity matrix. It's just ones, and remember this is the identity matrix for a 2 by 2. This is the identity matrix for a 3 by 3. I can just write a single subscript since these are square. They have ones on the main diagonal, zeros everywhere else. We said if we multiply a matrix by the identity, it's like multiplying by 1. Well, guess what? If I take a matrix and I multiply it by its inverse, I am going to get the identity matrix. So if I give you two matrices on a test, let's say A and B, and I ask you to determine if they are inverses of each other, all you have to do is multiply them together. If you multiply them together and you get the identity matrix, they are inverses of each other. Okay, so again, just to reiterate, to verify that two matrices are inverses of each other, you need to show that the product of the two matrices gives you the identity. Okay, so let's go ahead and practice that. Let's say I give you these two matrices and I ask you, are they inverses of each other? You're not finding the inverse of one and just seeing if it's the other. You're multiplying. So if I multiply these two matrices, what should I get if they're inverses of each other?
1, 0, 0, 1.
And do I get that?
No.
No?
Yes.
Yes, you do. Right? If you look at this, 2 times 2 is 4. 4 plus, oops, sorry. I circled the wrong one. 3 times -1, that gives me 1, right? Then first row, second column, if I add those, -3 plus 3 gives me 0. And then the 2, 1 position, second row, first column, 4 minus 4 gives me 0. And then again, I look at the second row, second column, and I get -3 plus 4 gives me 1. So it does in fact equal the identity, as will this, okay? So then you can say, therefore, A and B are inverses. So if you're verifying of each other, because A times B equals B times A, and they equal the identity. Okay? Now, these, again, if you were to verify, you would just multiply them on the calculator, or multiplying by hand, rather, because you can multiply a 3 by 3 matrix. You can check it on your own, and you should get the 3 by 3 identity if they are inverses of each other. So I'm going to leave that as an exercise for you. Multiply those two matrices together. Make sure you can get the identity. Of course, you can check all of these on the calculator. Now, any questions so far? No? All right. As we said, that identity matrix is the multiplicative inverse. The identity matrix is the multiplicative inverse. That you do need to know for the test tomorrow, or the quest tomorrow. So the multiplicative inverse is a square matrix, and it's just the identity matrix. We said that if you multiply any matrix by the appropriate size identity matrix, it's like multiplying by 1, it gives you back the original matrix. So knowing what I know about that, if I were to multiply A times I, what will I get back? What is the matrix I will get?
1, 2, 3, 4.
Exactly, which is just back A. Verify that on your own. If I multiply by that identity on the left, because we know that matrix multiplication is not necessary, it's not commutative necessarily. What should I get back?
1, 2, 3, 4.
Again, I should get back the identity. So it doesn't matter whether, the original matrix. It doesn't matter whether you multiply on the left or the right by the identity, it's still multiplying by 1. Now look at the next example. What is the order of the first matrix? Oh heavens.
1 by 2.
What is the order of the second matrix?
2 by 2.
Can I multiply these two matrices together?
Yes.
What is the order of the product going to be?
1 by 2.
And what is that matrix going to be? You should know.
1, 2.
Yeah, I should get back this original matrix, right? Because I'm just multiplying by the appropriate size identity matrix. Okay, let's look at the next one. Now, technically, when we're multiplying by 1, we're multiplying by a 1 by 1 matrix, the number 1. What is the order of the first matrix? It is a 1 by 1. What is the order of the second matrix? Anybody?
1 by
2.
2.
1 by 2. So if I have a 1 by 1 and a 1 by 2, can I multiply those together? Yes. And what is the order of the product going to be?
1 by 2.
And what is that matrix going to be?
1, 2.
Exactly. So do you see how that works with the identity matrix? Now, we talked about how to get the inverse of a matrix. We talked about how to get the inverse of a 2 by 2 matrix, compute the determinant, check to make sure it's not 0, and then to find the inverse of a 2 by 2, we did 1 over the determinant times that adjoint matrix, where we interchange the main diagonal and negate the elements on the cross diagonal. For a 3 by 3 or larger ordered matrix, you could put it in the calculator, but you can also calculate it by hand. You better believe you're going to need to know how to do this. How do you compute the inverse of any matrix, any square matrix, if the determinant's not 0? To do that, all you have to do is augment the original matrix A. So I'm starting with my original matrix A. I'm going to augment that with the identity matrix. So augment that with the identity matrix. I'm just putting the little bar there to show you that I've augmented the original matrix. So I am starting with, 1, 2, 3, 4. And I'm augmenting that with the appropriate size identity matrix. If it was a 3 by 3 matrix A, you'd have the 3 by 3 identity. If it was a 4 by 4 matrix A, you have a 4 by 4 identity. So does everybody understand how I have this original augmented matrix? Yes?
Yes.
Okay, so guess what you're going to do? If I'm starting with matrix A, augmented with matrix I, and I perform row operations, I will end up with the identity on the left, right? What we've known as the solution matrix for the coefficient matrix, the identity matrix. And what will be on the right-hand side will be the inverse of A. This is beautiful. And to verify that they are inverses, you can take that original A and your inverse you found, multiply them together, and they should give you back the identity. So let's do this together. Practice row operations. Let's take this original matrix here. Let's perform row operations and get it to the solution matrix on the left, the identity matrix on the left. So if I were doing that, I would leave the first row alone and somebody tell me how I'm going to get a 0 here. What row operation?
-3, row 1 plus row 2.
Beautiful. Okay, so let's look at what we have. I still have 1, 2, 1, 0. I haven't changed it. And let's perform that row operation on the entire second row, including that identity I appended. Okay, what is my new row 2?
0, -2, -3, 1.
Excellent. Okay, now let's say, and we need to be okay with fractions here. Let's say I want to get a 1 here. I'm not going to change the first row, but what would I do to the second row?
Divide by a -2.
Yes. Or multiply by a -1/2. I like to think of multiplication when it comes to matrices, but either way, they mean the same thing. Okay, so what is that going to give me? That is going to give me, I'm leaving this alone. I have 0, 1, 3/2, -1/2, right? And the reason I went ahead and did that is because, let me go ahead and write that a little bit better. And let me write this a little bit better so they line up. I now have, look, oops, this is a 2. I now have a good portion of this information. What's left to do? On the left-hand side of this augmented matrix, all I have left is to get a 0 here. How am I going to get a 0 there? I'm not changing the second row, but what am I doing to the first row? What row operation? This is a 2, right? What row operation am I doing to get a 0 here?
2 times R2 minus R1.
Okay, 2 times R2 minus R1. What is that going to give me? Give me the entire matrix. Give me the entire matrix. Anybody? 2 times row 2, 2 times 0 is 0, minus row 1. Now, did I want to do that?
You can do -2 row 2 plus R1.
I prefer that, yes. So I'm going to do -2 times row 2 plus row 1. What is my new matrix? Come on, y'all.
-1, 0, -2, and 2.
Mm-mm.
Oh. 1, sorry.
Very good. And then this didn't change, right? So now that I have the identity on the left, this is your inverse. And I could multiply this A inverse by this A and I'm going to get the identity, right? So you can do that with any matrix. Now, how do you put this in the calculator? Again, I'm going to leave that as an exploration. You enter the matrix, you go to math. The very first thing is DET. Verify that the things we did in class gives you those determinants. As far as finding the inverse, you put the matrix in the calculator, then you go to the button, little x inverse. You hit the inverse of the matrix, it will give you the inverse of the matrix if it exists. Okay, again, this is not on the quest tomorrow. It only covers up to what we were doing as of yesterday. But this will be on the test once we come back from Thanksgiving. Any questions? All right, y'all have a wonderful rest of your day. And don't forget, we have a math club meeting today after school. Math